Orthogonal projection is a concept of linear algebra, and it's similar to the Fourier representation of vectors in an Euclidean vector space. I have a video about Fourier-coefficients here on my channel. So if you are interested and need some extra knowledge, you can watch that video now or after this video here. Before we start with orthogonal projection, I want to remind you what an orthonormal basis is. So let V be an Euclidean vector space. An Euclidean vector space V is a vector space over the field of the real numbers together with a scalar product, which is denoted like that. A scalar product is a positive definite symmetric bilinear form. Let B is equal to B1 to Bn be a basis of the vector space V. The basis B is called orthonormal basis of the vector space V if the scalar product of Bi with Bj is equal to 0 for I is not equal to j, and the scalar product of each vector Bi in the basis B with itself is equal to 1. That here means that the Euclidean norm of each vector Bi in the basis B is equal to 1. The Euclidean norm of a vector x in the space V is defined as the square root of the scalar product of the vector x with itself. That norm is denoted like that. By the way, you can use the so-called Gram-Schmidt-orthogonalization process to find or construct such an orthonormal basis B. I have a video about the orthogonalization process here on my channel. You can watch it now or later if you want. Let's take a look at the orthogonal projection of a vector onto a subspace of an Euclidean vector space. Let V be an Euclidean vector space. Let U be a linear subspace of that vector space V. Let B is equal to U1 to UR be an orthonormal basis of the linear subspace U. So B is an orthonormal basis of U, not of V. Let small v be a vector in the vector space capital V. Then there are two options. V can be an element of the subspace U. Then you can write small v the following way. V is equal to the sum from k is equal to 1 to r of the scalar product of small v with uk times uk. That representation is called the Fourier representation of the vector small v with respect to the orthonormal basis B. These coefficients here are called the Fourier-coefficients. If you want to learn more about Fourier-coefficients, you can watch my video about Fourier-coefficients here on my channel. The second option is that small v is not in the subspace U. Then you can still consider that linear combination here. But the result will not be the vector small v again, but a different vector which we call small p, which is an element of the subspace U. That vector small p is called the orthogonal projection of the vector small v onto the linear subspace U. I want to point out that small p is not equal to small v in this case. Small p is an element of the subspace U, because it's a linear combination of vectors from U. The vector small v is not an element of U. So, the vectors small v and p cannot be the same. Here I have a picture that shows the orthogonal projection. So we consider the space R2 with the standard scalar product. The subspace U is that line here. That here is the vector v, which is not an element of the linear subspace U. That green vector, small p here, is the orthogonal projection of v onto the subspace U. You can also see why it's called orthogonal projection. The green and the orange vector are orthogonal to each other. So this here is the illustration of the orthogonal projection of a vector small v onto a linear subspace U. Let's take a look at an example. Our vector space V is equal to R2 with the standard scalar product. So the scalar product of a vector x with a vector y is equal to the first entry of x times the first entry of y plus the second entry of x times the second entry of y. That scalar product is called the standard scalar product of R2. We consider the following subspace U of R2. So U is equal to t times the vector 1, 1, where t is a real number. The subspace U describes a line. A basis C of that line is the vector 1, 1, which we call C1. So this here is a basis of the linear subspace U. For the orthogonal projection, we need an orthonormal basis of the subspace U, because the basis C only contains one vector. We just have to normalize that vector 1, 1 and have found an orthonormal basis of U. That means we have to divide the vector 1, 1 by its Euclidean norm. The Euclidean norm of the vector 1, 1 is equal to the square root of 2. So b is equal to that here 1 divided by the square root of 2 times the vector 1, 1 is an orthonormal basis of U. Because that vector here, which we called U1, has length 1. Now we consider the vector small v is equal to 0 and 2, which is not an element of the linear subspace U. Our formula now tells us that the orthogonal projection of the vector small v onto the linear subspace U is given by the vector p is equal to the scalar product of small v with the vector u1 times u1, where u1 is that vector in the orthonormal basis here. This follows from the fact that r is equal to 1. So we have to calculate that scalar product here, the scalar product of small v with the vector u1. The scalar product of the vector v with the vector u1 is equal to that here. So this vector here, 0, 2, is the vector small v. And that here, 1 divided by the square root of 2 times the vector 1, 1 is the vector u1 in the orthonormal basis B. When we solve this here by using the following calculation rule, we get that this here is equal to 1 divided by the square root of 2 times 0 times 1 plus 2 times 1. And this is equal to 2 divided by the square root of 2. Now the vector p is equal to that here. And when we plug in everything we know, we get the following. So this here, 2 divided by the square root of 2, is that scalar product here. And this here, 1 divided by the square root of 2 times the vector 1, 1, is the vector u1. We can rewrite this here a little bit, and in the end we get that p is equal to the vector 1, 1. So that vector p here is the orthogonal projection of the vector small v onto the linear subspace U. Here I have a picture where you can see what is happening. So that white line here is the linear subspace U. The orange vector is the vector small v, so the vector 0, 2. And the green vector here is the orthogonal projection small p of the vector small v onto the linear subspace U. Let's take a look at another example. Now the vector space V is equal to R3, together with the standard scalar product on R3. U is the subspace that has the basis B is equal to 1, 0, 0 and 0, 1, 0, which describes the xy plane. The basis B is already an orthonormal basis, because the vectors u1 and u2 are orthogonal to each other, so they have a scalar product equal to 0, and both u1 and u2 have Euclidean norm 1. So B is an orthonormal basis of the xy plane U. Now we have given a general vector V is equal to x, y and z that is not in U, and we want to find the orthogonal projection of the vector small v onto the linear subspace U. We will use our formula again to find the orthogonal projection P. In this case R is equal to 2. So the orthogonal projection P is given by the following formula here. We have to calculate these two scalar products here and there. So the first scalar product we have to calculate is the scalar product of small v with u1. This is equal to the scalar product of x, y, z with 1, 0, 0. So this here is the vector small v, and that here is the vector u1. And this here is equal to x, because we have to calculate x times 1 plus y times 0 plus z times 0. And in the end, this is equal to x. And the second scalar product we have to calculate is this scalar product here. so the scalar product of small v with u2. And this is equal to that here. So this here is the vector small v, and that here is the vector u2. In the end, this is equal to y, because we have to calculate x times 0 plus y times 1 plus z times 0, which is equal to y. So the vector p is equal to x times u1 plus y times u2, and this is equal to that here. When we rewrite this, we get that the vector p is equal to x, y, and 0. So this vector p here is the orthogonal projection of a vector v onto the xy plane. Just the coordinates x and y of the vector v and z is equal to 0. Here in the picture you can see what is happening. So that here is the vector small v. And this here, that shadow here, is the orthogonal projection p of the vector small v onto the xy plane. Let's take a look at a very important property of the orthogonal projection. It's the property that the orthogonal projection p is the best approximation of the vector v when it comes to the distance between the vector v and the subspace u. Let U be a linear subspace of the Euclidean vector space V, and let small v be an element of the space V. Let P be the orthogonal projection of the vector small v onto the linear subspace U. Then the orthogonal projection P is the unique vector in the linear subspace U that has the smallest distance from the vector small v. Or in symbols, the Euclidean norm of the vector small v minus the orthogonal projection P is equal to the minimum over all x element of U of the Euclidean norm of v minus x. So the orthogonal projection P is the unique vector in the linear subspace U that has the smallest distance from the vector small v. As I said before, that property is important. Here in that picture you can see an illustration of the property. So that green vector here is the orthogonal projection P of a vector small v onto the linear subspace U. That orange vector here describes the distance between the vector v and p. It's the vector v minus p. And you see, when you move away from this point p here to some other point x that is located in the linear subspace U, the distance between small v and x becomes larger. So this orange vector here really describes the smallest distance between the vector v and the linear subspace U. Okay, I hope you are now able to calculate the orthogonal projection of a vector onto a linear subspace. If you liked this video, please consider subscribing to my channel. That would help and motivate me to keep creating videos.